Well, you know, we have the triple pulse and the TRIPLEVERSE theory, for short TPT, and that's actually 3 pulses, and then the big pulse is what would be considered the Big Bang. So triple pulse, TRIPLEVERSE theory, 3 pulses, and then the last pulse, which is a big pulse, can be, you know, similarly be considered the Big Bang. We spoke about the strong nuclear force, weak force, electromagnetic force, and then we have a pristine force, because when the first NG band zone was expelled, when it cooled down, it formed a pristine force. So now that's the name we're going to call it, the pristine force, but we need to come up with a name. So now the NG, when the NG cooled down, a particle will be created, right? So we'll add that particle to the standard, the standard model, and the force there into the standard model. Okay, gravity is not a force, right? We spoke about the Pauli exclusion theory. We spoke about, I don't think we touched on quantum dynamics, but we will touch on that. Not now, right? So let's see. We spoke about quarks. Now, this is the main topic I want to talk about, but I just want to refresh your memory for a little bit. We have the singularity. We have the exterior pulse, right? So and then we have the inward pulse. So in between here, we're gonna have the strongest, the highest energy level, which would create the DNA or the characteristics in this field for the strong force, and the gluons, right? And the quarks. Because the quarks actually, you couple them together and you can form a neutron and a proton. So this is where the gluon would be, the genetics for the gluon would be created, and the DNA for the will be imprinted, right? For the strong force will be imprinted in here for the gluon. But let me just talk about the gluon for a second, right? Just for a second. The gluon is massless. There are eight different types of gluons, right? So if we do the pulse, the 3 pulses, this is a watered down scenario of the pulses. But this is like half cycle of the pulses that I am doing now. But if we were to truly do 3 pulses, it's going to be, an inward pulse, and then it cycles back outward. That's 1 pulse with 1 cycle. But if you only go this 1 inward pulse, that's going to be like half a pulse, right? To complete the pulse, it goes in, and to complete the cycle, we have to come back out. So if you do this 3 times, inward again, outward, inward again, outward, inward again, outward, right? So 1, 2, 3. This final pulse, right? That would we would call the Big Bang, because this is going to be the big pulse, and that's what we would consider the Big Bang, right? But in the Big Bang, I'm going to talk about the Big Bang in a minute. I just want to go through something real quick. Now, the gluon gluon is massless, and this is the force carrier for the strong force. But why is the gluon massless? The gluon is massless because it was created in this zone, and it was not contaminated by any other energy level. So the gluon is massless because because it's pristine, protected by the strong field around it, and it never interacted with the Higgs field, right? This is why the Higgs field would never interact with the gluon because it did not have the imprint on the field, on the gluon field, and on the Higgs field, vice versa. So the gluons would be massless. Same, I will discuss the photons, right? I just want to explain that to you why the gluons would be massless, right? And we have 8 different types of gluons. So I just want to say that. But the main topic right now, before I go, we will go forward with different videos. Main topic I want now to say, well, let's compare the Big Bang versus the TPT, right? Okay. Let's have a competition. The Big Bang says, this is singularity, that there's one expansion, Big Bang, but in this expansion there's a rapid one bang, and there was a rapid expansion, right? And they call it the cosmology inflation theory that speeded up, that created that rapid inflation. And then the cause of the expansion is because of the repulsive gravity force, right? That's what causes a rapid expansion in the beginning. Say 10 to the minus 34 seconds, it rapidly expands. Now, the Big Bang slowed down as we see it today because the repulsive gravity force decayed, right? So it decayed, and the universe as we know it slowed down. But 7 billion years ago, the universe started to speed up. So what's the answer for that, right? The repulsive force decayed and it slowed the universe down. And then 7 billion years ago, after observations, we find out that the universe now is speeding up. Well, now the repulsive force now kicks back in. Well, where did the repulsive force comes in? We don't know, right? So it came back in out of magic, whatever. But this is the cosmology inflation theory. And if you look at this theory, right, if you have one energy field, right, that expanded, right, where are you going to get, say, the quantum fluctuations, to create different forces and energies, right? You are just going to have one field that cools down, and maybe you're going to have one particle created by this one field that cooled down, or you're going to have one force, right? Because it's just a uniform expansion, right, with a uniform field. But this is a Big Bang. Now compare it to the triple pulse and triple verse theory, which states, okay, here we have the singularity, we have one pulse outwards, then it pulse back in, and then it pulse back out. But this is a simplified version. I'm just using half of a cycle of a pulse, right? So now, when this pulse outward, this spreads, so, it expanded outwards, right? And the strong field, the strong force will be created here with the gluons, right? And when it pulls back in, it squeezes that the area in, right? And it will create a higher energy field here, and the higher energy field will create a strong force, right? Like a gluon force carrying particle. So right away we have a quantum energy levels changing, right? To create these particles. This is just the DNA, right? So when it expands back outward with a pulse, when it pulls back in, right? So it pulls outward to this position, So when it pulls back in, now this energy fields are changing, and it pulses into part of this energy field, and this is what I call a band. You see, we have a band around it because it cannot pulse far inward because of the strong force field that's stopping it from pulsing all the way to the core, right? So we have a band of energy here, right? A band of quantum energy. So this band of quantum energy is a mixture. And the mixture now we can consider like I'm just saying where the electromagnetic field force was created, right? Because it's a mixture of energy levels. So even if you had the magnetic energy field different from the electric energy field, right? The two different fields, because of the pulse, they could mix. And in this band form the electromagnetic force. So you have a different field with a different field. So that's basically it. So now we pulse outward, they pulse inward, and now we pulse outward, and this is the Big Bang. The last pulse. Big Bang. So we see a lot of different levels of fields and bands. Sorry, my throat. Different levels of energy zones and energy bands, right? Different levels. So this is where these particles will be created. And also, if we, very briefly, if we have a pulse inward, we can have a positive charge, and if we pulse outward, we can have a negative charge. So we can see where the charges can also be created if this energy band was neutral, right? Where we will get that from. And the spin would occur when this energy field slams into this other energy field, right? And create a spin. But this is all, angular momentum into the field, right? But this is all the DNA for when you have the final big pulse, right? Will be projected when the universe cools. All of this different energy fields will cool, right? And whatever interaction and the DNA were imprinted on these fields will be transposed when the universe cools. So certain energy fields attract each other, like forces and particles, and we see the forces and the particles interact because of the DNA implanted in them during the triple pulse event, right? So the universe will cool down. The DNA of these fields are already implanted. We have some bands of a mixture. Like the electric and the magnetic can have a mixture combined, and this is where we would have electromagnetic force. Now we talk about the photons. The photons is massless, using the same concept as the gluons, which did not interact with any other field to create the gluon, because the gluon can interact with themselves, and did not interact with the Higgs field. The photons also did not interact with the Higgs field. It was protected by the electric field and the magnetic field, like it's being squished, right? But this is where the photon will have interactions with the electric field and magnetic field and the magnetic field. So that's that. So do the comparison. Let me know. You like the Big Bang, or you like the triple pulse and triple verse theory, TPT. Next time.